All right, another example in the energy methods in week 2 for vibrations, and this is one that comes from Dr. Bob's notes, although I redrew the thing. We want to find the effective mass of the spring. So this is an interesting one. So we're going to use the energy methods to be able to do this. So we know that sorry about that. Okay. We know that the kinetic energy basically is 1/2 m, and we're going to call something the effective mass, x dot squared, right? So this is, they're going to say, okay, before we ignored the mass of the spring, now we're going to include the mass of the spring, which are designated as ms, and we want to say, well, what kind of additional stuff is going to happen to the kinetic energy due to the spring. Right? We're not going to concern ourselves, well, it's not going to change the spring potential energy because of this, and we're ignoring gravitational potential energy. So it is really each little individual coil maybe, or we can have a designation dy of this thing. We can say, well, this coil up here, its velocity is going to be 0. This coil down closest to here is going to be the same velocity that we're going to have of the mass. And it's going to linearly be changing as you go past that thing. So what we could say is that the velocity, oh geez, my handwriting. It's like I don't want to have my palm on my on my screen here. So the velocity, let's pretend that says velocity, is linearly distributed. Linearly distributed. You know, and there's actually no real reason to say that you fully would believe that, right? But we'll go ahead and hit the accept button. Boing, I accept. And so what that means is that we could say, okay, if you wanted to have the express the velocity at any given point, you would say, here's your coordinate of where you wanted your velocity, and here's your L, right? So as you go up, you know, as you get to y equals 0, your x dot is 0. When you get to your y equals L, your x dot would equal to what the velocity would be at the mass. So there it is. So now let's try to find what is the additional kinetic energy that we would want to deal with, because we have to account for that the spring has mass, right? Well, first off, we get the 1/2, and then we would take the total mass of the spring, right? We were going to say, well, let's take the mass of the spring and say, here's a mass per length right there. So we've just distributed out for each chunk of mass. And maybe I should include this in a integral, because we're going to do this, and we're going to integrate from 0 to L. So like every little spot along the spring as we're coming down, we're going to have this little chunk of mass. So here's the mass, but we're doing it per length right here. So as we're doing it across the length as we're going through. And we're going to multiply by the velocity, and we said the velocity is going to be this y divided by L squared dy. So we can agree that these are a whole bunch of collection of all of the individual incremental kinetic energies that are going right there, and we're saying, okay, for each spot right there we have one of these things. But you notice that these are all constants. The only thing that's right here is y is the only variable. So I'm getting tired of green. We'll go back to this blue. So we do a little bit of monkeying around and go 1/1/2 and then ms, and you'll notice that x dot, it doesn't actually change with, you know, with position right here. So we could bring that out here, and the L cubed, right, because we had this L and then there's two L's right there, and then the integral right here of y squared dy, and we're going from 0 to L. And so it's not a difficult thing to get to, where we're going to go, I'll rewrite sum of this 1/2 ms x dot squared over L cubed, but we get 1/3 L cubed as part of our solution right there. So L cubed as part there, and we get 1/2 ms over 3 x dot squared here. And now we can, and I think Dr. Bob did this differently in his solution. Yeah, he just plugged it back in. I'm going to go ahead and use the thing that I called in the previous one, the value added approach right there, where we use the maximum. So if we say that T max equals U max, right? So in the T max we had 1/2 m x dot squared, but now we have the additional part of 1/2 ms over 3 x dot squared is going to be equal to 1/2 k x squared, and substitute that x is equal to big X, and x dot is equal to big X times omega n. We gotta shift another color here. I'm gonna go with the dark red. I like the dark red. But anyway, let's see. Boom, boom. We could have crossed that out anyway, and gathered these things together with m plus ms over 3. And then I'm losing my mind. I'm going to do big X squared omega n squared, because I'm replacing the x dot squared right there, equal to k times big X squared. And purple. Boom, boom. Solve for it. Get the square root of k over m plus ms over 3. What does it mean? All right, so here's the answer. So what? Huh? The big idea here is that only 1/3 of the spring is really being affects the natural frequency result. So it's like the effective mass of the spring is 1/3 of the spring, and not the whole spring is included in the calculation. This happens in a bunch of different areas, so it's worth exploring in other scenarios, right? That we could see, well, like, okay, how much? Because we often say neglect the spring, neglect the mass of the spring. Well, here we go. Well, maybe if the spring has a lot of mass, we want to include it. Oh, how can we include it and not make the problem too complicated? Well, using this energy method can bypass that complication. So that's what we have here, and we will make another video, because that's what we do, we being me.